If you recall, we've been setting up double integrals and we've been using rectangular coordinates. The thinking is the same kind of thinking that we had way back with single integrals, where we were calculating area is equal to length times width, where length was a function, the width was the dx. Now, instead of finding the area under a curve and above an interval, we are calculating the volume under a surface and above a region. The integral calculation is going to be the function giving us the height, and dA is going to be some small rectangle in the region. Since we were using rectangular coordinates, I was breaking up the region into little rectangles with length dx and width dy. So the dA was written as dx times dy, or dy times dx. The picture from above, we would have some region. And we'd have some dx. In this case, I'm going to have a gigantic dx. Times dy. So this is our view from above, and this rectangle here is the dA. So that dA is some small part sitting inside the region R. We're assigning to that dA one value of the function to flatten out the top so we get this little rectangular solid, and we can find the volume of that rectangular solid with the height times the length times the width, the height times the area. The height given by one value of the function, the area given by the dx times the dy. Our challenge was to be able to describe in the integral parts what's x between and what's y between. So that's what was going on in the integral parts. The integral over r, this part is just telling us what values of xy we're plugging into the f of xy dA. That's all the values xy that we're going to plug into f of xy dA. All the different places we're going to evaluate this. Plug in all those values, add them up. Little bit weird question because we're adding up over a continuum. There's nowhere to put the plus signs, but that's why we have antiderivatives and the fundamental theorems of calculus. In this case, we were describing the region with x and y. We were describing the dA as these little rectangles because we were using rectangular coordinates. We need to think about what this looks like in polar coordinates. That's another way of describing two-dimensional space. The reason that we want to do that is sometimes we want to describe something what is round, and using rectangular coordinates for round things is rather inconvenient. It leads to things like trigonometric substitution. And even though that's everybody's favorite, we still want to maybe try to avoid all that work. So let's do this in polar coordinates. So now let's describe R2 with polar coordinates. Apparently, I'm shouting everything today. So either that or I'm just factorial things today. Probably a too much coffee problem. So in polar coordinates, instead of describing a horizontal distance and a vertical distance, we describe one distance and an angle. So polar coordinates look like r and theta, where r is the distance from the origin, or the pole, and theta is an angle in standard position. Specifically an angle in standard position and measured in radians. The main reason that we want to use radians is that radians has some kind of relation to the size of the circle. That's what radians are for. Degrees are arbitrary. We picked 360 degrees because it was divisible by a lot of stuff. 360 is a really great number. It's divisible by a lot of stuff, but it is super arbitrary. We just picked it. There's nothing really related to the circle about 360 degrees. Radians are related to the circle. So that's why we want our angle in standard position to be in radians. Radians aren't as arbitrary as degrees. So like we could have said, going around the circle, that's 100. 100 is a terrible freaking number. Divided by 2, no problem. Divided by 4, no problem. Divided by 8, 12 and a half is fine. 12 and a half is fine. Divided by 3, come on, man. 0.3 repeating. Terrible, terrible. 360 is divisible by so much more stuff. I know we don't get to 7, but you know, who cares about 7? So that's why we need radians in this case. So from a picture standpoint, I'm going to go in the first quadrant here. First of all, we're going to start by putting the pole at the origin, because that's the only thing that makes sense. We didn't have to do it this way, but it's the only thing that makes sense. I've been to the universes where they didn't do this, and everything is just a complete mess. It's even worse than like the people that are still using Roman numerals. That universe is terrible. Logistics is awful in those universes. So when we describe this point as xy, this is a thing that we're familiar with. We have a horizontal distance x, and we have a vertical distance y, two distances. And then we describe this as xy. If we want to describe this as r theta, we have one distance, the distance from the pole to the point. So we have one distance. And an angle. We have that distance and we have the angle theta. So the coordinates of this point are either xy or we can write this as r theta. the two sets of coordinates, we can translate in between those two sets of coordinates. They are related to each other. And we can just grab this little right triangle that we've drawn here with the opposite of x and a adjacent of y, hypotenuse of r, and an acute angle theta. That acute angle theta can be used as a reference angle in all four quadrants. So it'll suffice just to go over this once in this first quadrant. So we can write r as a function of x and y by saying that r is x squared plus y squared is equal to r squared. So we say r is the square root of x squared plus y squared. This is how we can get r if we have x and y. That's how far we are from the origin or the pole. And then theta in terms of x and y, we could use tangent. Tangent of theta is y over x. Opposite over adjacent. If I want theta, then I can just do a tangent inverse and make sure that I'm in the correct quadrants. So we can do tangent inverse, but we have to pay attention to what quadrant we're in, because tangent inverse is only going to return things in quadrant 4 and quadrant 1. So we got to make sure that we're in quadrant 2 or quadrant 3, that we get our theta in the right quadrant. If you want x in terms of r and theta, then x is adjacent, r is hypotenuse. So we could say x is r cosine theta, and y is r sine theta. So if we have polar coordinates, we can write rectangular coordinates. If we have rectangular coordinates, we can write polar coordinates. What we get when we use r and theta as graph paper is much different looking graph paper. Rather than just a grid of horizontal and vertical lines, all evenly spaced apart, we now have concentric circles and lines coming out from arrays, lines going through the origin. All the lines are going through the origin on this graph paper, and then it's just a bunch of concentric circles moving out. So the problem that we run into is that if we want to make a little rectangle, if here is the origin, the problem that we're going to run into is that theta is not a distance. Theta is an angle. So if I have dr and d theta, I'm not describing an area. Dr is a length, but d theta is not a length. I jumped like right to the conclusion. I went here, remember polar coordinates? And then like skip like several years later, double integrals, because that's what we care about today. So the problem that we are run into that we need to address is that theta is not distance or length. Theta ain't going to be measured in meters. D theta is not going to be meters. So I can't just take d theta and stick it into an area. I need to make theta into a length. So the problem is theta is not distance and length. So dr d theta is not area. That's the issue that we run into. Notice that if I have a d theta, when this spreads out over a bunch of r's, the farther we are from the origin, the bigger that length is going to be. And it's going to be curved. Now, between those two values, we definitely have a length with dr. That's no problem. But this is what we want. We want an area for dA. The farther we are from the origin, the longer this side is going to be, or this curve is going to be. Fortunately, we know how this is going to work. We're just calculating the arc length, and we all know how arc length works because we know what the circumference of a circle is. So if we want d theta to be a length, we do need to consider how far we are from the origin. So we just need to know this distance r. So now that arc length is r times d theta. So the arc length is r times d theta. Questions? That's how we turn theta, the d theta, into a length. Everybody's looking at me like this. Because you're like, oh, dude, that's still fucking curved. That's still a problem. But we're going to make d theta really small. If we make d theta really small, it ain't going to be that curved. Think about American cars from the 70s. Tolerances were pretty wobbly. It's fine. It's fine. So if d theta is small enough, we can approximate this little piece of the region with a rectangle. I know that this one, this end of the rectangle is actually going to be larger because it's further away, but dr is also going to be really small. So if we keep d theta real small and dr real small, we can approximate this with a rectangle. So it's just kind of a curvy rectangle. So the dA is going to have not just d theta dr. D theta dr, that's not an area. Dr is in meters, but d theta is in radians. No help. But if we multiply the d theta by r, that's what we use for dA. So in polar coordinates, dA is r d theta dr. We need that extra factor of r to make d theta into a length. And we're going to keep them small enough that that curvy rectangle is rectangle enough. If this feels very hand wavy about how we set this up, that's only because it's very hand wavy in how we set this up.
Exactly.
Yeah, so that is correct. So if you're like, this feels a little bit hand wavy, that is correct.
Like, calculation, like, really fine.
So arc length, we already know that arc length is r times the angle because we know the circumference of a circle is just arc length when theta goes all the way around, when theta is equal to 2 pi. So recall circumference is 2 pi times r. This is just arc length with theta equal to 2 pi. So the circumference is just the arc length going all the way around. So if theta is equal to pi over 2, that's just that quarter of a circle. Arc length for a quarter of a circle. So we have a region in rectangular coordinates we can set up this double integral f of x, y, dA in rectangular coordinates where we have dy dx. Or we could set it up with dx dy. Or we could do this in polar coordinates. Now we're going to have to convert our function of x and y to some function of r and theta. So we'd have to rewrite the function in polar coordinates. And dA is not just d theta dr. I need to have an extra factor of r that turns d theta into a length. We have an extra factor of r that turns d theta into length. Yeah, it's taking the trig. We're doing a trigonometric substitution, and we're going to avoid doing the trigonometric substitution in here by doing the trigonometric substitution before we even begin. That way, the mechanics work out in our favor.
When you pick the fix up, so you don't.
Right. You do a trig sub early, so you don't have to do the trig sub in your integration step. Do your trig sub before you even begin, rather than doing your trig sub in the middle during the integration phase. That's when it's messy. But you're right, it is just trigonometric substitution. Trying to hide that. You've been doing trigonometric substitution all along. That's the Palmolive bait and switch. No one's seen that commercial for decades, so. There used to be a commercial because like Palmolive was like, had like oil in it, essentially, palm oil in it, because we want to destroy the environment. But it made like your dish soap not so harsh. It used to be like when you wash dishes, your hands were just wrecked if you wash your dishes a lot because the soap is really hard, right? And it destroys your skin. It doesn't do that anymore because we decided to put like other stuff in it. It's like, well, what if we made this so it didn't dissolve people's skin? And companies for a long time was like, oh, but it's poor people that wash dishes, so why do we care? And then once more people started doing it, it's like, oh, maybe we should just like soften this up a little bit. And then we're like, oh, thank you. And then dawn, it's like, oh, we're environmental. Because you wash birds. Yeah. What are we talking about? So the important thing to note is that this extra factor of R shows up as part of the dA, but it gets integrated along with the function. So if I wanted to rearrange this, I'd still have f of R and theta, but the R stays with the part that we're integrating. So even if I switch the order dr and then d theta, we need that extra factor of R to turn d theta into a length. Extra factor of R to turn d theta into a length. But even though it shows up as part of the dA, it stays with the f that we're integrating. And that extra factor of R goes with the f when we're integrating. Oops. Polar coordinates are really good at describing round things. Yesterday, we described a region that was x squared plus y squared equals 9, everything less than x squared plus y squared equals 9, that circle. And it was very messy because we set it up in rectangular coordinates. We should not have been surprised. We're describing a round thing with square coordinates, big mess. We had to do trigonometric substitution. Rather than doing the trigonometric substitution in our integration, where it's kind of a pain in the butt, let's do the trigonometric substitution now and convert this to polar coordinates. So if we want to describe this region, when we look at this region in polar coordinates, we can just take R from 0 to 3. We'll just pick a point here. Start at the origin. This is where R equals 0. And go out to R equals 3. And then just take theta equals 0 and go all the way around to theta is equal to 2 pi. In polar coordinates, this circle is two intervals, r from 0 to 3 and theta from 0 to 2 pi. That circle is just two intervals in polar coordinates. So if I wanted to integrate a function over this circle, polar coordinates would be the way. Now, we would have to convert our f of x, y to a function of r and theta. So one of the things that we'll have to do is rewrite our function in polar coordinates. If we're in polar coordinates, the dA has to include an extra factor of r, but the region is just two intervals, theta from 0 to 2 pi, and r from 0 to 3. Or the other way around, and it's easy to switch the order because these are just two intervals of constants. Integral from 0 to 2 pi, integral from 0 to 3, f of r theta times r dr d theta. Now our integration is going to be super easy, barely an inconvenience. If I integrate the function 1, this should give us the area of the circle. There I am shouting again. If we replace the function with just the constant function 1, that should give us the area of the region over which we are integrating, in this case, a circle. So if we integrate from 0 to 3, the integral from 0 to 2 pi, the function 1 is in polar coordinates, so I need r d theta dr. In this setup, the first thing we're integrating is a theta integral. So this will be the integral of r d theta is r theta. I'm not going to do color coding anymore. It's getting too intense. So first I'll do my theta integral. The antiderivative of r with respect to theta is r times theta. We evaluate from 0 to 2 pi. So we get 2 pi r minus 0. The integral of 2 pi r with respect to r is pi r squared from 0 to 3. Just like we expected. We change the order around, we get the same value. So if we go from 0 to 2 pi, and then from 0 to 3, or other way around, I guess, r dr d theta. Now we're integrating with respect to r, so that'll be a 1/2 r squared. Evaluated from 0 to 3. And then we still have to integrate from 0 to 2 pi d theta. We can see we're going to get the same thing. This is going to be the integral from 0 to 2 pi of 9/2 d theta. So I'll have 9/2 theta evaluated from 0 to 2 pi. The 2 cancels out the 2 down here, and we get 9 pi. Because when you integrate the function 1, you get the area of your region. Because we did the problem in polar coordinates, d theta is not length. So I have to multiply by r to make d theta into a length. That's the r shows up as part of the dA, but gets integrated with the function. Any questions? How's that, okay? Also should note that the x squared plus y squared is r squared. So this equation becomes r squared equals 9, which means r equals 3. So that's the equation of this circle. R is equal to 3. Theta does not show up in that description, which means just use all the values of theta. Any questions? Comments? Slide remark? Everybody remember polar coordinates? To do polar coordinates in trigonometry? Maybe.
I remember for coordinates.
It's a tricky question to ask because polar coordinates will tend to show up in a trigonometry course. And one thing that happens is that if you start taking calculus like after high school, you might not have actually had a trigonometry course. That's kind of like the frightening thing. You like walk into a calculus class and then the instructor's like, hey, remember trigonometry? And you're like, oh, sure. I walked into my first calculus class having had 3 weeks of trigonometry. Because my high school was like, oh, let's just cram that into algebra 2. So I was like, oh, trigonometry is easy. We covered the whole thing in 3 weeks. And then they were like, oh, double angle identities. I'm like, oh, identity what now?
Double angle identity.
And the professor's like, oh, well, we're gonna have to use the double angle identities. You remember those, right? I'm like, are you having a quiz on this right now? And the professor was like, oh, no. I'm like, well, then yeah, totally, I remember this. Then I had to go to the library and get a trigonometry book because I didn't have the internet. Back in the Stone Age. Because I'm old. That's the joke. All right, so this is double angles in polar coordinates, or sorry, double integrals in polar coordinates. We did the same stuff. We're just using a slightly different language, but we can translate between the two. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.
Have a nice day. See you tomorrow.
See you tomorrow.